change the title of my talk a little from what it said in the program. I'm going to talk about pretty much the same talk, just a little bit more specific in the title. Effects of temperature on repeatability of fitness trajectories in microbial eukaryote, tetrahymenophilus. So I start out here with this this tree of all life. We know there's a whole bunch of variation that's evolved over the past 4 billion or so years. And we know these changes are stochastic mostly, and this is going to make evolution less repeatable. But we also know that the environment can shape the way these changes happen through natural selection, and that perhaps will make evolution more repeatable. But we also know that as the changes build up over time, you have a different phenotypic environment, and that's going to make evolution less repeatable. You're going to see things in this branch of life responding differently from things in this branch of life to the same evolutionary pressures, just because they're starting off vastly different genotypes. So the questions I'm going to address today are sort of broadly, to what extent is evolution repeatable, and then more specifically, how do initial historical differences between populations are affected by temperature as evolution progresses. Also, how does temperature affect repeatability from a single common ancestor? And then I'm going to talk a little bit about whether we see our symmetrical correlated responses at the alternate temperature. And then I haven't included this bit in the talk before, but I'm going to try and squeeze it in. I think this audience will be able to keep up. Hopefully I'll have time. Talk about how the fitness components differ across the temperatures. Okay, so when I mentioned historical differences and how evolution is going to, or how different temperatures may impact the way historical differences change as evolution progresses, this is sort of what I'm talking about. Things can either converge together, your initial historical difference could be maintained as evolution progresses, it could become exacerbated, or they could flip, and one of them may end up on a more extreme or higher growth rate. And when I talk about repeatability, I'm basically talking about the similarity in the growth rates, and whether so on top things are more repeatable, obviously, and then on the bottom things are less repeatable. And this kind of gets back to Gould's replay experiment. Replay the tape of life at the beginning is things can evolve the same way, or we're going to see drastically different outcomes. Okay, so I'll talk about the methods that I use to do this. We use it to experimental evolution in Tetrahymenophila. It's a large, free-living microbe. You can just sort of barely make them out with the naked eye. It has a complex life development and life history, which I won't be able to talk about today, unfortunately. But they're good for experimental evolution because they can divide pretty quickly in the lab, at least up to 7 times a day. And they can also be frozen in liquid nitrogen, although it's there's some issues with that. Okay, so every day I transfer I'm using 2 temperatures, and so at the hotter temperature we transfer, it's about a 100 dilution, and colder temperature it's about a 1 in 20 dilution. So we get 3 to 3.5 generations a day at the colder temperature, and about 7 generations a day at the hotter temperature. And we set it up so that at both temperatures the effective population size is about 100,000. So the colder ones, they start out a little bit denser every day, and they don't quite reach the same density as the 37-degree populations. And the basic design of the experiment is I have 3 different starting genotypes. There's an A genotype, a B genotype, and then a cross between the 2. And we have 4 replicate populations in each of these conditions so 4 at 24 degrees, and then 4 replicate populations for each genotype at 37 degrees. And everything is being assayed at both temperatures. So we can track the fitness in the home environment and in the alternate environment. And we measure fitness on a microplate reader like this. I basically have a plate running constantly, so every few generations we'll do replicates of 4 populations on the plate, and we get growth curves. And so we get pretty good fitness assays from the growth curves. side. So this is 4,000 generations at either evolution temperature. The red dots are assays done at 37 degrees, and the blue dots are assays done at room temperature. And the main takeaway from this is that you see this sort of classic decreasing rate of return that we see in evolution experiments. As things get fitter, fitness tends to increase less quickly. So I said at the beginning I was interested in the historical differences, initial historical differences between the populations. And so one of our populations, the A population, it started out significantly slower growing than the other two populations, which I'm showing in the first panel. This panel here. But after 3,000 generations, that difference is mostly gone at 37 degrees. These are the result of two heat tests, and you can see that this no longer significant at 37 degrees, where it is at room temperature. I should say that this is, it was maintained even for surprisingly long, that difference at 37 degrees. If the populations were all following the same sort of course of diminishing returns epistasis, we would have expected them to catch up much quicker. So there's something that's preventing them from catching up as fast as we would have otherwise predicted. And it still happens more quickly at 37 degrees than at room temperature. And by 4,000 generations, they seem to have caught up for the most part, although there may still be some. Okay, so in terms of repeatability or the variance between the lines, when we look at the variance component nested within genotype, so it combines all of the genotypes together, we can see that it's higher amongst the populations of all the 24 degrees, suggesting that there's less repeatability at 24 degrees and more repeatability at 37 degrees, which I think is sort of neat. And if we look at the variance component between all of the populations without nesting within genotype, so looking at the total variability, what we see is that gradually, there's a sort of increase at the beginning in variation like we would expect as things diverge, but as the populations converge, as the divergent genotypes converge back together, the variance between everything eventually goes down. However, we see that the 24-degree populations have a much bigger, higher peak, and it's later because they're converging, the different genotypes are converging more slowly at room temperature. This is showing the mean growth rate at 37 degrees on the y-axis and the mean growth rate at room temperature on the x-axis. The ancestors are all down here. The different colors are the different genotypes, and the closed circles are the ones evolved at 37 degrees and the open circles at 24 degrees. And you can see that the 37-degree populations cluster much more tightly up there. And the sort of interesting thing here is that there's an asymmetry in the correlated responses. So populations evolved at the hotter temperature, they increase their fitness at room temperature basically just as well as the ones evolving at room temperature. But the populations that have evolved at room temperature, they don't necessarily increase their fitness at 37 degrees to the same extent that the populations evolving at that temperature do. Which I think is interesting as well. Okay, so to summarize what I've told you so far, populations evolved at 37 degrees, for the populations evolved at 37 degrees. So I didn't mention this before, but they also have a higher growth rate after 1,000 generations. I mean, and that includes at the alternate temperature as well. And they have faster convergence, there's more repeatability, and there were stronger correlated responses on growth rate at the alternate temperature. So clearly the temperature has a big impact on evolutionary trajectories in these things. And perhaps hotter is better. So now I want to talk about how the different fitness components differ across the temperatures. So on the y-axis we have the maximum optical density, and then on the x-axis is the Rmax, which is the fitness component I've been talking about up until now. organisms have pretty different relationships. So each point represents the mean of 4 replicates from that genotype and evolution condition. And you can see here that it's very, there are these nice linear relationships within an assay temperature. So within an environment, these things seem to be highly correlated. But across environments within a given genotype, they always seem to be negatively correlated. But interestingly, also the populations that evolve at 37 degrees, they tend to have a less steep curve here, or a less steep pitch rather. So they vary more in Rmax and less in optical density, whereas if you evolve at room temperature, you vary more in optical density and less in Rmax, which I think is also kind of interesting. Okay, so I might have gone a little fast. Anyways, repeatability of evolution is dependent on temperature at which the evolution occurs. The hotter environment appears to result in more repeatability and more convergence. The correlated responses across temperature are asymmetric. And R and K are positively correlated within an assay temperature, but they're negatively correlated across assay temperatures, which I think is interesting as well. And I have future work that's going to try to look at more sort of varied environments and get a sense of whether this is something that's specific to the temperature environment or whether these relationships play out like across a bunch of other environments as well. And I want to thank my lab, the Zufall lab, my advisor, and everybody in the lab that's helped out on this, and my committee. And with that, I can take any questions.
What other environmental stresses are you thinking of?
I have a bunch of populations that are evolving in salts, ethanol, citric acid, DMSO, all sorts of things. There's about 15 of them. The problem is there's no replicates, so it has to be like sort of a global picture as opposed to specific to these environments. Yep.
Have you done any sequencing to get a sense of the genes involved in this?
Not yet. When I started out, that was definitely something I wanted to do, but there's so much to do just with fitness and fitness components that I kind of got distracted and I feel like sequencing is a little bit, like until we have a really good sense of how fitness is working, I don't want to get into the nitty-gritty details of what's going on at the molecular level yet. But definitely I would like to at some point.
What's the temperature in the natural environment that you think they'd likely face?
It's gonna probably range from the hot temperature I have down to below the colder temperature. They survive in like ponds in New Hampshire in the wintertime.